Yes.
Great. Thank you. And yeah, welcome all to our masterclass. I'll go right ahead and present our speakers, myself and Rogier. We are both senior scientists from DTU, Wind and Energy Systems in the Resource Assessment and Meteorology section. And we are both working on developing windkit and PyWAsP. And just some background on what that is. These are two Python packages for wind resource assessment. And one is PyWAsP, which is our API to the core WASP libraries, which is this industry standard tool used for a lot of wind resource assessment for flow modeling. And windkit is our open source Python library that PyWASP builds upon, where we define a lot of the open structure, like the data structures, I/O, and other things are in windkit. And one sort of thing about PyWASP is that it's connecting to the WASP core, which is the same set of Fortran libraries that sit behind the WASP GUI that is used in the industry. So a little bit of background on that. And then about the course we're planning. So this is this masterclass is some sort of a teaser for the real meet, which is the course that we are having in May from the 4th to the 22nd. And this course will be 3 weeks. It'll be semi-synchronous. So we'll have a mix of live sessions, and we'll try to accommodate different time zones. And then it'll be self-study with notebooks and videos. And we try to target two audiences, people who are knowledgeable about wind resource assessment and want to dive more into the programming side of it, and people who are programmers or coders and who are more interested in getting some domain knowledge and direct experience with working with wind resource assessment in code form. And then by the end of the course, we have a final project, which is optional, but where you get to do an automated wind prospector. So just a little teaser, and here's the QR code on the right. You can scan to take you to the website. And just to give you more of a taste of what this course contains or what you'll go through, we have these 7 modules, and it'll take you through the sort of Python toolkit. So the ecosystem of open source packages that is used a lot. And here we focus especially on X-Array. And then we'll teach you about windkit and PyWASP. And then in the preceding modules, we'll look at wind data and wind climates, terrain data, GIS, and then flow modeling and diving into PyWASP, wind farm and wake modeling, diving more into pywake, which is another Python tool developed here at DTU for turbine interactions. And then we'll look at AP, losses and uncertainty, and doing validation and reporting. So that's a little bit of a tease for what the courses will teach you. And we have some prerequisites for this course. Ideally, you need to have a little bit of experience and background with Python. Some of the basics we're not going to teach you, so you have to either study before our course or know this in advance. And we would also like you to already be familiar with some of the scientific ecosystem like NumPy and Pandas and so on. And actually, especially X-Array. If you're unfamiliar with X-Array, either you need to do a little bit of studying before the course or maybe reconsider. And it's also good if you know a little bit of statistics and, of course, wind resource assessment concepts. You don't have to be an expert, but at least some of the basic concepts are good to know in advance. And then in particular, you need to run some code on your own machine, a laptop or whatever machine you want to work on. And we can support Windows 11 and Linux, the x86 platform, not Mac or ARM at this point. So just be aware of this, that you need access to a Windows 11 or Linux x86 system. And then we have some people asking, are they sort of ready for this course? And we try to make some self-assessment to allow you to determine in advance if the course is right for you. So we have these questions like, can you write a function that reads a CSV and compute the mean of a column? Can you index a pandas data frame by date range? Can you explain what a viable distribution is? Can you say why we want to include in uncertainty for AP estimates? And if you can say yes to these, then yeah, you should be sort of ready to tackle the course. So that was a little bit of a idea of what it takes. So for today, the masterclass, we have two presentations, one by me and one by Rogier. I'll be talking about automating WREYA, and I'll try to explain what that abbreviation stands for. And Rogier will be talking about programmatic modeling of wind resources. And yeah, we'll take 15, 20 minutes each, hopefully, and then you'll have time for more questions afterwards. So I'll go ahead and dive right into automating WREYA. So WREYA is, of course, wind resource and energy yield assessment. And then the subtitle here of this presentation is from mast to megawatt hours programmatically. So it's really about some perspectives on automating this whole workflow or pipeline that is done when people do pre-construction WREYA. So what's the problem? What are we sort of aiming to do in this WREYA workflow? So on the right here is just an illustration of some turbines we want to put up somewhere. What are we trying to estimate here? We're trying to estimate some AP number, some distribution actually of AP, our best estimate of the distribution of AP at the turbine locations, so we can make a good economic estimate and get a loan from a bank or whatever to do a wind project. And typically, the sort of the things you have available to help you with this are typically measurements from mast and lidar. You have reference model data, like reanalysis data, maybe even mesoscale data or other sort of reference data sets. You have a sort of collection of tools and models, and they have methods. So that's very broadly the WREYA process and the available toolkit. And making a bit of a caricature of the current state, maybe, but maybe only a little bit. Today, this process is done as a sequence of work done in graphical user interfaces, and then passing data from one graphical user interface to the next one, and then maybe combining that with in-house methods and spreadsheets and so on. As I said, it's maybe a bit of a caricature, but not too much. And that's what we want to do a bit differently in a more programmatic way that is composable. So we want to be able to basically version control and document everything in a sort of a composable scripting setting where everything becomes very sort of reproducible and clear, and less prone to errors and sort of human issues. And speaking of that, here's the maybe provocative last thing. It should maybe be agent ready. Maybe not exactly these kinds of agents, but it's hard to follow the news without sort of seeing how AI coding, and these agents are basically eating the software world and running more and more of the processes that humans used to do. So just for illustration, I have added this this graph that shows the number of commits to GitHub that are made by Claude Code. So it shows this rapid increase in the number of agent commits to GitHub just from one of the agents, you could say. And this is actually at this point 4% of all of the commits on GitHub were made by these coding agents. So that's one thing that we should consider in the future, that our software is ready to be used by agents, and basically facilitate WREYA becoming doable by coding agents or by AI agents. Okay, so looking more in detail on this WREYA pipeline, I mean, WREYA is, you could say, the wind resource part and the energy yield prediction part. And the wind resource part is where we go from mast to a gross yield by reading in this raw data measured from a mast or from LiDAR, and then going through sort of a cleaning step where we take the raw data and obtain clean, ready time series, which we could call the site wind observations. We have to make this short-term measurement campaign representative of a long-term wind climate. So we have to do an MCP step, which is this long-term extrapolation. And then we take that long-term representative climate and move around from the mast location to where we want to put the turbines, which we do by this flow modeling step for vertical and horizontal extrapolation of the wind climates. Then we have a gross yield estimate from that, and that's what we take for our energy prediction pipeline here. And this is where we want to add losses and uncertainty. So we have first a wake modeling step where we add the wake losses and take the gross yield to the potential yield. And then we add further real world losses like electrical losses, availability, and so on, to get a net yield. And then finally we add some uncertainties to that and get an uncertain yield in the end, which is what we can bring with us to the bank. Okay, so now I'm going to go through these different steps and try to talk about from a programmatic perspective or automation perspective, what's sort of the current state and challenges of each of them. So if we start with the QA/QC step, what it does is we try to take the raw measurements and get clean analysis ready time series. So we want to filter out icing, failures, tower shadow, and stock sensors, anything that isn't representative or is a sort of an artifact of the way we did our measurements. And typically, yeah, as I mentioned, this is done in GUIs, and there isn't really a let's say mature and sort of ready platform for doing this through scripting. So there's an opportunity, I would say, to make a platform for scripting this that is sort of more mature than the current situation. So if we go to the next step, which is the measure, correlate, predict, as MCP stands for, then of course that is all about taking our measurements, which are typically 1 to 2 years, and correlating that to a long-term reference data set. It could be ERA5 or MIRA2 or another data set like that, and then extrapolating from this short period with our correlated data to a long-term representative period that's more like what we expect our lifetime to be of our wind farm. And why does it matter? It matters because, I mean, this interannual variability, so basically the uncertainty of having any 1 or 2 year measurement period as opposed to 20-year, can be quite large. So if we don't do this, we're risking a huge error made because of this, and it can even be bigger than these numbers I put here. And again, this is typically done through some GUI, and there isn't really sort of a unified or mature framework for doing this in scripting. So there's also another place where there's an opportunity to basically make this more programmatic and agent ready, you could say. And we are developing windkit, so I have to tease basically pump my own book, as they say. So with windkit, we have some options for doing long-term sort of corrections. One I show here is linear regression MCP in 12 sectors, and this is how this API looks like in windkit for doing that. Okay, I'll move on to flow modeling. So this is where we account for the local terrain effects on the wind climate and move from the mast to where we want to put the turbines. And of course, this matters because, the local variation in the wind climate can be quite large. So we need to account for these local effects. And here I have just a satellite picture of Østerild in Denmark, which is the test site, national test site, where we see these platforms. If you can see my mouse, I hope you can. But I'm pointing to these sort of sand-colored areas where the test sites are. And then you see the surrounding area, you see patches of forest and small hills, and there's a body of water out here. And then what I'm showing here is just WAsP or PyWAsP estimating how this wind climate varies with these local terrain effects. It's higher over water, it's lower over forest, and so on. So showing how big a variation you see and how you can sort of use WAsP to capture this. And here again, WAsP is the sort of standard, I would say, and we have PyWAsP that sort of enables you to do this in a more sort of scripting way. Just to tease the API, you can see how easy it is through PyWAsP to do this. But of course, there are still some challenges, especially you have to sort of be careful with the maps you use of the terrain, and if you want to do more complex sites with complex topography, I mean, it can be more. The linearized models in WAsP can be insufficient, and as soon as you have CFD, it becomes more complicated. And you'll hear more about this from Rogier in his presentation. I'll try to maybe speed up a little bit. And then we go to wake modeling, and I call this like a tooling success story. This is because, I mean, we have seen sort of a small explosion of like open source wind farm modeling tools in the recent years, like pywake and Flores and Foxes. So actually, this is one area where it is sort of possible to do your wake modeling through the scripting, and the tooling, I would say, is relatively mature. But of course, scientifically, there are still many questions inside this realm. And just to stress again how important this is, you need to account for the wake effects because they can be quite large, like 10% of your AP. So the challenges that are in this space are like the modeling soup problem. There are many models you can choose from, but how do you choose the right one? Validation gap, there's a limited number of public available validation data sets to use. Blockage, it's like a relatively new concern, so that's the sort of upstream slowing of the wind due to the bulk wind farm, and models there are still evolving. And then there's the site specificity. How do you sort of know when to choose what model? And just to illustrate sort of how sort of the tooling is very nice these days. Is a small example of using pywake to run a wind farm simulation. It's quite clean, I would say. And then the last thing is this losses and uncertainty part, where we basically take and add the losses, that's like the real world losses, on top of the wake losses that we got from the wake model, like things like availability losses, electrical and other losses. And then we also add the uncertainties from various sources to the estimate to obtain a more conservative estimate that the bank will let us lend money on. And here it's sort of very judgment heavy, so it's a bit hard to automate, and there's no sort of open scripting API as far as I know. But with WindKit and PyWAsP, you can do this. So we offer at least one solution for doing this in a more sort of programmatic way. And this is just an example of how it looks like with WindKit and PyWAsP. So that brings me through this sort of pipeline. I just want to quickly summarize some sort of take-home messages. There's sort of a maturity paradox that if we have clear physics, then APIs become also maybe cleaner. And as soon as we have more judgment-heavy steps, it's harder to automate. It's more like, you have to use your judgment more. Then for a lot of you, I mean, I would say that there's a lot of opportunities. I mean, as I tried to illustrate, there's unsolved problems and places where we don't have like really well-established frameworks for doing programmatic WREYA. So it's a chance to get in there and add something. And then, of course, I want to say that during the course, we can explore a lot of these opportunities further. And then the final sort of provocative bullet is about these agents and how the tools we build today will become the skills, as they call it, through which the AI systems can do the wind resource assessment in the future. So a bit of a provocative one, but I think it's gonna happen. And then I just want to end on the course slide again. So if you didn't get a chance to grab the QR code before, you can do it again here. Otherwise, I'm gonna close down and hand it off to Rogier if you're ready.
Yes.
I'm gonna stop sharing.
Can you see my screen? I hope so.
We can.
Okay, good. So I will take over from Bjarke and I will go a bit more into the details of what is actually happening in the flow model in PyWASP. So basically what we're trying to answer is a question like this. So we have somewhere a met mast in our landscape, and then we have locations for future turbines so that we want to know the resource of. And then the question is like, how do we use that measured wind speed and extrapolate it horizontally and vertically to the turbine locations? That's sort of the use case that the whole PyWASP modeling is built around. So as Bjarke was already explaining, it looks like this, but it's good to repeat it a little bit. So there's windkit, which is defining data structures and I/O and GIS things. Then there's PyWASP, which is just an interface to the WASP model that has been around for many years. And WASP is just like a normal GUI WASP that you may know, and that is, for example, also implemented in WindPro. It's a licensed software, so for that you will need a license. And then there's also from PyWASP, there's a plugin to pywake, so you are able to do wind farm wake modeling. So if you're familiar with WASP, you probably have seen this figure at some point. So it sort of shows the main modeling principles, what you try to do in wind resource assessment. So you start always from an observing climate, as Bjarke has also mentioned already. Then you try to remove microscale effects around your mast so that you get a more general wind climate that you are able to extrapolate to your turbine locations. And then using this generalized wind climate, you try to add the microscale effect at another location, and you will get a predicted wind climate. And then if you also do the wake modeling, you can get the AAP of your wind farm. But so what I will illustrate in this presentation is a little bit how you can think about this process in program calls. So usually you would do all of this in a GUI, and for doing this whole process, you would have to click a lot in a program. But the new thing about WindKit and PyWAsP and the ecosystem is that you can do all of this programmatically. So this diagram here may look a bit complicated, but it's essentially the same as this figure with the two arrows that I was showing before. So you will start with a wind climate that you might have measured on this meteorological mast, and then you just have wind speed and wind direction as a function of time. And then in PyWASP and WindKit, you can easily then transform that into information about what we call bind wind climate, which tells you sort of how much wind there is at a certain location, and that is easy to visualize and use in WindKit and PyWASP. And then if you want to do that process, you can just go to the documentation from PyWASP and WindKit and then look up the calls. So I'm talking here about a bind wind climate, and this is a time series wind climate. So we convert from the time series to a bind wind climate. And then you can imagine that in this call, you can pass in the main object, and then there's a lot of options to sort of customize this process. So just to explain a bit more then how PyWASP is doing wind resource modeling. So that you always have to start with providing maps, and this is also something that we will do in the course, as Bjarke discussed. So here on the left, I've just shown an elevation map from an area somewhere with quite complex terrain and a coastline. And one of the models, submodels that is implemented in WASP is the IBZ model, as we call it, the orographic model, because from experience in flow modeling in terrain, we know that generally over hills, you have a large speed up, and there's a model implemented for that in WASP. So then if you would create a orographic speed up map for the map here on the left, and it would look something like this. So for each of the sectors that I was just showing, the wind direction sectors, you can actually let the model calculate speed up effects, and that you can use to go through your generalize and downscale wind PyWASP workflow. And then you can see that, for example, over this high rich areas, there will be speed ups. So these are indicated in red. And that was sort of the directional aspect, but then there's of course also an aspect of orography in as a function of height. So here I'm just showing how the orographic speed up changes as a function of height. So it also has a height dependency, and that is modeled in PyWASP. Then another model that we use is the internal boundary layer model. So that is accounting for surface roughness changes. And another piece of information that you have to always do in your wind resource assessment is making a land cover map or a roughness map, where you say like what is the roughness length of all of your land cover types in your area. And that is what is shown here on the left. So you will create this map for a certain area that you're interested in, and then the simple model that is implemented in WASP is this internal boundary layer model, which just calculates speed up effects as a function of the downstream distance of a roughness change. And the way that is done is through what we call roughness rows. So that's again one of those programmatic things that you have access to in your workflow. And what that tells you is just which roughness changes are important for my site of interest, so that you can sort of visualize and inspect them, and you know what is happening in the model. And then if you do something similar as what I was showing for the orographic speed-up effects, it will look like this. So again, we have the wind direction coming from different directions, and then you can imagine that the coastline acts as a big roughness change when the flow is from north to the south. So if you pay attention to this arrow and you look like when the flow is from north to south, then you will see that when the flow is going inland, that there's like a speed down in the wind compared to what it was offshore. And so this is also one of the submodels that is available in PyWAsP and that you can easily visualize in Python. And again, this was the directional aspect, but there's also a height aspect. So you can imagine that as you go higher up in the atmosphere, sort of the effect of the roughness change becomes smaller and smaller because the flow gets sort of blended and more mixed. So that's what you see in this figure in the left. If you go higher up, the speed-ups approach 0. So then if you do this in a programmatic way, you know now the orographic speedups and the roughness change speedups. So then you can have a call like this, which is called get side effects. And that will give you all of the effects for your site of interest based on the maps that you have provided. And then one core piece that you may have heard about is the logarithmic wind profile and the geological drag law. And these are just modeling tools implemented in WASP that allow you to transform from your wind climate from one place to the other. So for example, if you're measuring over a sea and you want to go estimate the wind speed over land, then you can use these formulas to do that process. And this is sort of a core foundation of the model. And the way that is doing that is by estimating an effective roughness based on this roughness roses that we talked about. And then you can easily transform the wind speeds. And again, that can look, for example, like this if you plot that. So then we have done all that, and then one key step in that you might have known from WASP already is the generalized step. So you create this generalized wind climate that I was talking about, which is supposed to be valid for large areas and is general. So then in PyWASP there's a call like this, generalize, and then you have this wind climate that you can use for estimating your predicted wind climates. So, and then once you have this, you use the same laws to go down and make a surface layer wind, and then apply the speed ups at another location. And then finally, what you get out is a predicted wind climate, and that you can do with this downscale function. So, and here, typically, your output locations will be, for example, your wind farm. So like, let's say 20 turbines that you're interested in. And you can also do this whole process directly. So you go from the wind climate directly to a predicted wind climate at some other location. There's functions for that as well. And so then you can choose what you want your output as. For example, a histogram of wind speed and directions, or Weibull distributions is a function of wind direction as well. So this all sounds nice, of course, but there's some things that WASP is good at, and some things that it's not good at. So it's very good in sort of simple terrain with moderate orographic effects and a lot of roughness changes. But then some things that are not explicitly accounted for in the model is, for example, mesoscale effects and effects of very complex terrain. But for that, there is routines implemented to analyze CFD results. And there's also ways of combining WRF data that we will also talk about in the course. And these form the foundation of, for example, the Globe Wind Atlas and the European Wind Atlas that you might have heard about. So in those wind atlases, what we use is actually PyWAsP, so the model that you're also going to use in the course. And then so quickly something about the validation of the model. So the nice thing about PyWAsP is that there's a lot of papers around it, and recently, or actually this paper is currently in review, I think. We did a benchmark with many other participants from the industry. And it was nice for us to see that actually comparing all the models that PyWASP was actually one of the best, even though it was sort of a benchmark which included WRF and LES and all kind of other models that take much more computational resources than PyWASP. But still, it turned out that PyWASP was doing very well at this site in terms of how well it could predict the AEP of a big wind farm in the US. So if you're interested in this, then keep an eye out in the Wind Energy Science journal, where this paper might come out soon. And the other thing is that we are sort of continuously validating the WASP GUI. So it has been very well tested in the last 40 years that it has been on the market. So all the time when we are working on the model, we have a large validation set of wind masts all around the world, and then we try to make sure that each version of the model is better than the previous version. So that's just a nice advantage of the development that has been going on for WASP, and therefore also in PyWASP. So on the figure on the right here, you can see different versions of WASP, starting with WASP 12.6, and then on the y-axis there's the mean absolute errors in wind speed, and you can see that just by updating the WASP version, you get automatically a better model, and the absolute errors in wind speed are getting lower and lower. And this was vertical extrapolation, and then you can also look at horizontal extrapolation, where you see quite similar patterns. So that was all I had to say. This is just to show you again the course overview and the QR code for the course that you can scan if you want more information. And I think with that, I will hand off to Bjarke if he has anything else to say, or open up for questions for the audience.
No, I think we have many questions, so we could just go ahead with those.
Yeah, you can just dive in the questions. And probably the first question we can answer is, can we share the presentation slides with the participants afterwards? Because someone said he would like to have the slides to justify his boss to pay for the cost, which is very good. If the company can sponsor.
In that case, of course, we can share them.
Okay, yes, so I can answer the questions now, then the presentations will be shared afterwards together with the recordings. So now, we have around 20 minutes to answer the questions live, and the teachers will pick them and answer them as many as we can. Yes, so I will give the floor to the teachers.
Should we take turns over here?
Yeah, sure.
Let's see. I'll pick one then. So there's a bunch of people who ask whether they have to pay for a WAsP license if they take the course, or a PyWAsP license. And no, you do not. You get a PyWAsP license for the course, so you don't have to pay any extra licenses for the course. We provide everything.
Yeah, let me also find one. I can see for here in PyWASP, is there mesoscale data available in South America? Good question. I guess yes, from the Global Wind Atlas. There's data available because that's global data, so you could use that.
And then Sergio asks, is the automatic digitalization lines definitions, file format changes, or orography and roughness included in PyWASP? I mean, not exactly sure. Maybe Sergio, you can write again. I'm not exactly sure what the question is. Do you know what automatic digitalization is, Rogier? I mean,
No, but I mean, maybe we can say that there is a QGIS plugin which you can use for making maps yourself, like by digitizing and clicking on a map, and there's also interfaces for downloading data from public land cover data like Corine and World Cover and many other sources, and these are available in this plugin, but also in WindKit itself. So you can just get the data directly in your Python session.
Then I'll grab the next one. Can you submit jobs to WASP CFD directly from PyWASP? Not yet. You can ingest a WASP CFD result if you have a result you made from the GUI, and then you can use it in PyWASP. But it is something that we are considering adding so that you can directly basically query a WASP CFD result and get it back in PyWASP. But at the moment, you cannot.
Yeah, and can we access external CFD files in this workflow, like Flowres from Methodine? In principle, yes. You just have to sort of adopt the file conventions that we use, or the variable names that we use, and as long as it's a gridded area, you can use it as an input in PyWASP.
Then there's some questions about, let's say, non-stationary effects like low-level jets, and there's one asking about sea breezes, whether it can capture that. And I mean, no, I mean, WASP is a sort of steady model, so it doesn't capture these dynamic effects. And I mean, it's doing the modeling as a wind climate, so you could say that if the effects are in the measurements and you're not moving too far from the mast, then you sort of have that effect already. But it cannot sort of capture these dynamic effects if it has an influence that differs from where the mast is to where the turbine is.
Yeah, and somebody's asking, can we apply air density corrections? And yes, just like all the calls that I was showing from PyWASP, there's a call called get air density, and then it will just give you the air density for your output locations.
How well will this toolchain work for regions like the lower latitude Caribbean? That's a very good question. I think join the course and let's find some measurements from the Caribbean and see how well we do. It's I don't know exactly how well it does, or let's say the specific challenges in the Caribbean. But yeah, I'm not sure.
Yeah, and some people ask about the title of the paper, but I think the editor still has to accept it for public review. So.
And then one question about how much time do you have to finish the final project? So maybe I can reiterate that in the course you have this optional final project that you can do. So you basically have to create a script or a notebook by the end of the project that is like an automated wind prospector where you get some mast data in, and then you have to estimate some AP numbers for prospect turbine locations. And the idea is that you have to hand in this final project by the end of the 3 weeks. So we start, if you choose to do that, you feel like you have the time to do it. You start already the second week and then finish it by the end of the third week. So someone was asking if they had 12 months. The idea is that you finish it very soon. I mean, in this time span of the course. So that also means it's not going to be a very very broad thing. We just want it to be a short, self-contained thing that you develop during the course. Do you have one, or should I grab another one?
Yeah, I was just scrolling down in the list of questions, but it's endless. So
Yes. Francesco asked, will the course touch also pywake? To what extent? We will be touching pywake. We have this module on the wind farm and wake effects. So there we will touch it. So it'll be, let's say, 1/7 or 1/6 of the course will focus on that. So it will be a small corner of the course.
And then does Pyro support losses computation such as BET in the wind sector or grid curtailment? Do you remember that, Bjarke?
Not sort of explicitly, but we support that you, let's say, if you have the numbers yourself and if you have the Excel sheet with your expected losses, you can apply them, of course, in PyWAsP. But we don't have any sort of support for you to get those loss numbers.
And is the WASP license different from the PyWASP license? Yes, it's a different license.
Can we change the type design of wind turbines based on the wind change profile distribution to have better results? I mean, you're sort of, yeah, I mean, sometimes we'll maybe in the course we will tell you what turbine to use. But if we have an assignment that is more open and more about maximizing AP, whatever, then of course you're free to optimize the turbine type. Yeah, I don't know. That needs still to be ironed out.
Yeah, and does WindKit include quality control routines, and are they validated? No. You have to, like, that process is supposed to be done outside WindKit using pandas data frames or other tools to filter your data.
And then there's one about logarithmic profile versus power law profile. Maybe you can take that, Rogier.
Can also be power law profile. Yes, that has recently been added, I think. There's shear extrapolation functions available.
What about after the course? Do we need license if we want to use PyWASP after the course? Yes. So then you'll get access to PyWASP for the course, and maybe we'll add some buffer around the course so you can get started before the course and you can play around with your projects for some time after the course. But at some point it will stop working.
Yeah, the questions keep jumping for me.
Yeah, so I talked about the prerequisites and the self-assessment for the course, and we'll hurry up and add that information to the website also, so that you can see it there. So check back on the website in a week or two, and then you will find the prerequisites and the self-assignment and some links to external resources where you can read up on some other things for like X-ray or so on. So check back on the course website.
Yeah, and Gareth is asking, can we convert a TIFF file for roughness into the native map format? Yes, that's possible. So it has conversions for raster to vector and vector to raster and land cover to roughness and yeah, all kind of conversions that you might want to do. They are available as functions.
As an anonymous, maybe an agent writing, how fast does an agent burn through PyWAsP credits? Yeah, let's see. There's one. Alexandru is asking, maybe unrelated, but I see that there are different tiers of PyWASP subscriptions. Could you provide an average number of runs required to run a medium-sized project for a few masts, let's say 10 to 15 wind turbines? Well, because you can batch your calculations, you can do it all in actually 2 runs. So with the lowest tier, you get now I don't remember the number off the top of my head, so I'm not even going to say a number, but you have several thousand runs, and you can batch a lot of calculations into 1 run. So you can do everything in 2 runs because we have this methodology in WASP where you have a generalization step and a downscale step, and each of them require 1 run. So a full extrapolation of your wind climate to all your turbines will require 2 runs. So that means you, in principle, you can do thousands of wind farms in that way.
Yeah, are you considering extending the validation to more eastern regions of the Mediterranean Sea? Yes. I mean, if we get the data, it's we try to be as complete as possible.
How is the compatibility of PyWASP with WinPro, as is the case with standalone WASP license, which works as the back engine for WinPro? So if I'm not mistaken, you can read several WASP formats in WinPro, and you can also work with these WASP formats in PyWASP. So if you can write it from PyWASP, you can ingest it into WinPro. So there's a little bit of a compatibility, but yeah, it's limited by the file formats, I would say.
And does WindKit have a file conversion from WRG to ASCII? I don't remember that.
No, not currently, but that's if there's a demand for that, we can add it to the list. Is there a displacement height calculator on PyWASP, or is the displacement height have to be added manually? Yeah, maybe you could take that for here.
Yeah, yes, that's included. So if you provide yeah, you can make a map with a displacement height, and then it's automatically used in PyWASP and used for your flow calculations. So yes, it's implemented.
Does PyWASP have a layout optimization module, either starting from a predefined layout to reduce number of turbines, or aggregation algorithm to reach n number of turbines? And no, we do not. So we would recommend something like TopFarm for this kind of workflow. So yeah, you have to sort of know where your turbines should be in PyWAsP.
And how expensive it is to end-to-end wind resource assessment in PyWAsP. Yeah, I think that was sort of answered already by you before, Bjarke, right?
Yeah, it's basically what's the cost of the bronze license, and actually, what is the cost of the bronze license? Now I need to to check that. But it's let me get
I can answer another question in the meantime. Are
yeah,
there
I'll find the
some
number.
publicly available resources detailing the wind climate extrapolation methodology used in WAsP? Yes, but it's a bit of I mean, I think many papers are listed on the website, wasp.dk. But yeah, I mean, we are a research institute, so we are publishing papers when we implement something new. And but WASP has been developed for 40 years, so there's many papers available that deal with WASP. If you want to know more details.
1,500 euros is the cheapest tier if you want a PyWASP license for 1 year. Yeah, so there's one person, Swapna, asking about, I come from a coding background. I'm not familiar with wind energy terminology. Where can I learn some of the terminology and basics of wind energy? And we'll also give you some links in when we update the website where you can go. For example, there's a massive online course that made by DTU on Coursera, which could be a good primer. I mean, that goes through many parts of wind energy, including wind resource assessment. But maybe you can just watch the wind the energy assessment part as a primer for this. Sergio asked about layout optimization. I think we already answered that.
Sorry to interrupt because actually we are running out of time. It has been 1 hour. Bjarke and Rogier, do you want to take a couple minutes more to answer more questions? Or we can end it here and then people can write to you if they have more questions directly.
I mean, we could do a few more minutes and then wrap up.
Okay,
So
alright.
let's do 2 more questions and then we can wrap up.
Yeah.
Let's just. I'll try to search through and find a good one, and then you can do the same over here.
Yeah. Somebody's asking, I used already pywake for wake modeling, but it was very slow for big wind farm. Is speed processing better in PyWASP? I think it will be the same as pywake, but it depends which wake model you're using. I think what is the speed of it. So there's many options in pywake. And somebody asking, is PyWASP bankable? That's also a good one. I would say yes, because it gives you exactly the same results as WASP, and WASP is bankable. But you will have to talk to the bank to confirm that.
How does pywake compare with the wake models currently implemented in WindPro, such as N.O. Jensen wake model? So at least I can say for the WASP part, you can use pywake through PyWAsP to get your wake effects. And when you do that, we configure pywake so it gives identical results as the WASP GUI, the park wake model there. I'm not exactly sure how that differs from WinPro exactly, so I couldn't speak for WinPro.
Okay, I think we answered even more than 2 questions. And the time is up, and we were so happy to see that many of you are very interested in the course and have so many questions, like flooding to the teachers. As Matthias wrote in the chat, we have shared the teachers' email addresses. So if you have some course-specific questions in this knowledge domain, you can write to the teachers. But you have some questions about, administration, the payment, and other general questions, you can write to Matthias directly. You can also find our contact information directly on the course page. Yeah, so I would say that thank you all for today. I really hope you enjoyed your time with us. And if you are interested in learning this topic, please remember to sign up. And I will repeat myself again because it's the first version, so we offer a discount of more than 50%. And next year, when the second version comes up, it will be increased to regular price. And we have a seat limit of 25 students, and some seats already sold. So if you have any further questions, please just don't hesitate to contact us.